Here we're going to look at two problems from the Mathematical Olympiad of Moldova. And I'm not going to give hints this time because I think any hint that I could give would give it away really too quickly. So we're just going to jump right into the solutions. If you want to try the problems, go ahead and pause the video and then give them a go. Okay, so both of these come from the year 2000 edition, and the first one is question 2. We'll do that one first. So we want to solve in R. So in other words, we want to find real numbers x and y satisfying this system of nonlinear equations. So we've got 36x squared y minus 27y cubed equals 8. And then we've got 4x cubed minus 27xy squared equals 4. Okay, so maybe the first thing that I see when I look at this is that I can reduce this to a system of homogeneous differential equations by taking twice this equation and subtracting this equation. So let's maybe write that like this. We'll do 2 times equation 2 minus equation 1. That'll have the effect of doing this. 2 times 4 is 8, minus 8 is 0, so we'll get a 0 on one side of the equation. And I chose to do it in this order so that I could have my coefficient of x cubed positive, although it doesn't really matter. Okay, so let's see what that gives us. So we'll have 8x cubed, so that comes from multiplying this by 2. And then we're subtracting this guy right here, so that'll end up being a plus 27y cubed. And you'll see why we're doing it in this order in just a second. And then next, we'll have a minus 54xy squared, and then a minus 36x squared y equals 0. Now let's see if we can factor that. And actually we can factor that using the sum of cubes formula. So maybe we'll recall that real quick, that if you have a cubed plus b cubed, that's going to be equal to a plus b times a squared minus ab plus b squared. And so in fact, we have a sum of cubes here, seeing this as 2x, the whole thing cubed, and seeing this as 3y, the whole thing cubed. So that means we can factor out these first two terms using this formula, which I have up here in pink. So let's maybe go ahead and do that. That'll give us 2x plus 3y, and then we'll have 4x squared, 9y squared at the end. And then in the middle, we'll have the opposite of the product of these two, so that's going to be minus 6 times xy. So just to reiterate where that came from, we got that from factoring these blue parentheses up here. Then next, we can factor by grouping in this next term. So notice we've got a greatest common factor of 18 times x times y. Maybe we'll take out a minus 18 times x times y just to make everything positive inside. Let's see what that's going to leave us with. So 36 divided by 18 is 2, and that's going to leave us with 2x because we've got an x squared. 54 divided by 18 is 3. That's going to leave us with a y. So we have plus 3y, and this is equal to 0. So just to reiterate, this came from factoring out of these two terms in the orange parentheses. But now we're set up really well because we have a greatest common factor among all of these terms, and that is 2x plus 3y. So we can go ahead and take that out of the whole thing. So let's go ahead and do that. So 2x plus 3y. And then what are we left with? Well, here we're going to have 4x squared. And then we'll have minus 6xy minus another 18xy. So that's going to be minus 24xy. And then finally plus 9y squared. That equals 0. So that gives us two equations that could be equal to 0. Either 2x plus 3y equals 0, which tells us that y equals minus 2/3 x. So that's one possible relationship between x and y. Or we could have this 4x squared minus 24xy plus 9y squared equals 0. But we can solve that using the quadratic formula, maybe solve it for y using the quadratic formula. So we're going to think about this as capital A times y squared plus capital B times y plus capital C equals 0. So this is like our C term. This right here is like our B term, and this right here is like our A term. So notice the C and B term have an X component. Now inserting this data into the quadratic formula, so we'll have negative B, that's going to be 24x, and then it'll be plus minus the square root of B squared minus 4 times A times C. So I'm going to skip to the chase here, and that is 432x squared. So all of that's under the radical. Then we need to divide that by twice A, so that's going to be 18 in this case. Okay, so that's what we get for our value of y, but we can actually clean that up quite a bit. And we can do that by noticing that this 432 is actually 144 times 3, and 144 is, you know, a well-known perfect square. It's 12 squared. So we can extract that from the square root, and that'll leave us with 24x plus minus 12x. So I'm taking this x squared out of the square root 2. I really need to include a plus minus, but I already have one there, so that's okay. And then next is going to be the square root of 3, and this is all over 18. Okay, so now we can do a little arithmetic simplification on that, but I won't worry about that. I'll just arrive at the top of the next board with this thing simplified a little bit. On the last board, we determined that the relationship between y and x was one of the following setups. So we had either y was negative 2/3 x, or y was equal to this thing, which wasn't written like this on the last board, but I've simplified it like I said I would. So it's 4 plus minus 2 root 3 over 3 times x. And I'll call each of these numbers maybe alpha plus minus. So alpha plus will be 4 plus 2 root 3 over 3, and alpha minus will be defined similarly. So now we want to work down each of these cases in concert with one of our original equations, and we can pick either one we want in order to find a final solution here. So let's maybe work down with this second equation. So let's see, we'll have 4x cubed minus 27 times x times y squared. So notice y squared in this case will be equal to 4 over 9x squared, and then we need this to be equal to 4. So notice we've got a simple cubic equation that we can use to solve for x. So let's see some simplification that can happen here. So this 9 can cancel this 27 down to a 3. And then we're left with 4x cubed minus 12x cubed equals 4, like that. 3 times 4 is 12. So that's going to give us a minus 8x cubed equals 4, which tells us that x cubed equals minus half, which tells us that x equals minus 1 over the cube root of 2. Great. And then similarly, we can plug this into y, and we'll see that y is going to be equal to 2 over 3 times the cube root of 2. Maybe there's some rationalization of the denominator that you could do, but I don't find that super necessary in this case. So this is our ordered pair of our solutions. Okay, sweet. Now let's go ahead and move on to this next setup. So I'll do the alpha plus case, but the alpha minus case is going to be exactly the same. So again, we'll plug it in here. So we'll have 4x cubed minus 27 times x times y squared, but that's going to be alpha plus quantity squared times x squared, and that needs to be equal to 4. Okay, so we have that. Good. Now let's see what we can do from this. We can maybe factor an x cubed out of the left-hand side of that equation, and that's going to leave us with 4 minus 27 times this alpha plus squared, where again alpha plus is that kind of gnarly number. Now this is going to be equal to 4, but that allows us to solve for this x pretty easily. It's going to be in terms of a lot of crazy square roots, but that's okay. We'll have x equals, it'll be the cube root of 4 over 4 minus 27 times this number, which I've called alpha plus squared. So that's our value for x, and then our value for y is clearly just alpha plus times that. So I won't write that in. Okay, good. So we finished off this problem. Now we'll go ahead and clean up the board and do this second one. So we just finished off this first problem. Now we're going to look at this second one, which is question 4 from the same exam. Our goal is to find polynomials p of x with real coefficients, although I didn't write that here, satisfying the following functional equation. So we've got 1 plus p of x equals p of x minus 1 plus p of x plus 1 all over 2. Okay, so first off, I want to notice that the degree of p of x must be bigger than or equal to 2. And I want to do that with the following observation. So if p of x is a linear polynomial or a constant polynomial, in other words, it's of the form ax plus b, where a and b are any real numbers. So notice that could be a constant polynomial if a was equal to 0. Then you can easily check that p of x plus 1 is going to be equal to ax plus b plus 1. Wow, I mean, that's straightforward. And then p of x plus 1 plus p of x minus 1 over 2. Well, let's see what that is. So that's going to be equal to a times x plus 1 plus b plus a times x minus 1 plus b all over 2. But that simplifies pretty easily, and it simplifies down to ax plus b. But ax plus b and ax plus b plus 1 are not equal. So what that immediately tells us is that the degree of p of x must be bigger than or equal to 2. And in fact, there's a big hint built into this. And that hint is this observation right here, that this object, this p of x plus 1 plus p of x minus 1 over 2, is equal to p of x itself, not p of x plus 1, if we have a linear type polynomial. So that'll actually be pretty helpful, and we'll use that observation at the end. But at the moment, all we have is that the degree of p of x is bigger than or equal to 2. Okay, well, let's start with that. So on the last board, we argued that the degree of p of x had to be bigger than or equal to 2. In other words, we can expand p of x like a sub n x to the n plus a sub n minus 1 x to the n minus 1 all the way down to a0. Now what we want to do is suppose that p of x satisfies this equation. So we have 1 plus p of x equals p of x plus 1 plus p of x minus 1 all over 2. Now the trick here is we want to extract coefficients of the same power of x from both sides of the equation. And you might think, well, which power of x? And that actually requires a bit of playing around. But after playing around with it for a little bit, you'll see that extracting the coefficient of x to the n minus 2 is actually the most helpful. So let's maybe give these guys some names. So I'll call this left-hand side LHS for left-hand side, and this right-hand side RHS for right-hand side, just for shorthand. And then I want to extract coefficients from each side of the equation. So the coefficient of x to the n minus 2 in the left-hand side of this equation, well, notice that's the coefficient of x to the n minus 2 in this 1 plus p of x. So that's going to be equal to, well, it's actually equal to 2 different things depending on the value of n. So that's going to be equal to a sub n minus 2 if n is strictly bigger than 2. But if n is equal to 2, then this represents the constant term on that side of the equation. So it'll be a sub n minus 2 plus 1. And this is if n equals 2. Good. Now let's go ahead and look at the coefficient of x to the n minus 2 on the right-hand side. So coefficient x to the n minus 2 on the right-hand side. So that's going to be 1/2. So I'll just take that 2 in the denominator and factor it out. And then this breaks into some pieces. So that's going to be the coefficient of x to the n minus 2 in a sub n times x plus 1 to the n plus x minus 1 to the n. Great. So we'll have a coefficient of x to the n minus 2 in that binomial expansion of each of those. And then we'll also have one So in the next term down and the next term down. So the coefficient of x to the n minus 2 in a sub n minus 1, x to the n plus 1, x plus 1 to the n minus 1 plus x minus 1 to the n minus 1. And then we've got one more place that we can find terms that are up to x to the n minus 2, and that will be the a n minus 2 terms. So let's write that down. So here we have plus the coefficient of x to the n minus 2, a n minus 2 times x n plus 1 to the n minus 2 plus x minus 1 n minus 2. Then maybe let's go ahead and end these parentheses. We can actually calculate each of these pretty easily. So this is going to be equal to 1/2. And then notice that the coefficient of x to the n minus 2 here will be equal to n choose 2. And then here it's equal to n choose 2 times -1 squared. And that -1 squared is really useful because -1 squared is 1. So in other words, the coefficient from this bit right here, so I'll put a orange star, that'll be equal to 2 n choose 2 times a sub n. So that's what we have there. And then from this term, we will have n minus 1 minus an n minus 1. And that's because it's n minus 1 choose 1 plus n minus 1 choose 1 and then -1 to the first power from expanding that binomial. But those are going to cancel. So that's really important. We don't get anything from this right here, so let's maybe denote that by this thing goes to 0. Good. And then notice from this, we just get the top two terms. So that's going to be equal to 2a sub n minus 2. Good. So let's see how this simplifies. So that's going to simplify to n choose 2, a sub n plus a sub n minus 2. So maybe I'll just go ahead and bring this right to here. Okay, so we just determined that the coefficient of x to the n minus 2 on the right-hand side was n choose 2, that binomial coefficient, a sub n plus a sub n minus 2. But next, we want to use the fact that these two are equal to each other. So let's notice that we have two cases here. So case number 1 is that n is bigger than 2. But if n is bigger than 2, notice that the left-hand side of the equation is a sub n minus 2. And then the right-hand side of the equation is going to be n choose 2, a sub n plus a sub n minus 2, like that. But we can cancel these from both sides, and we'll get a 0 on one side of the equation. So what that tells us is that a sub n equals 0. But that means that we were not dealing with a degree n polynomial in the first place. Maybe we should have been careful about pointing that out here. We can take this n to be the smallest such that a n is not equal to 0. But that gives us a contradiction right here. So what have we done? We've contradicted the fact that n is bigger than 2, but that means that n has to be equal to 2. So that'll be our case number 2. N equals 2. And we know that like n can't be equal to 1. In other words, the degree can't be equal to 1 or 0 from what we did on the very first board. So now let's notice if we have n equals 2, what this thing turns into. So the left-hand side will be a sub n minus 2 plus 1. Or I should say this is a sub 0 plus 1. And then the right-hand side will be equal to 2 choose 2, a sub n, but that's going to be a sub 2. And then plus a sub n minus 2, but that's 0 in this case. Good. So now comparing this side and that side of the equation, we see that a sub 2 equals 0. So at the moment, what we see is that the polynomial has the following form. It is of a degree 2 polynomial, so it can't be larger than degree 2 because that gave us a contradiction. Can't be smaller than degree 2 because of what we did on the first board, so it has to be a degree 2 polynomial. The leading coefficient has to be 1, but we have no information about the rest of the coefficients. But it turns out that the rest of the coefficients are free to be anything. So in fact, right now, all we know is that P of X is the form x squared plus ax plus b, but then I'll let you guys do this. You can check that these all work, which isn't super clear until you start forcing this equation to hold with this type of polynomial. And that's a good place to stop.